Hello. Yeah. Good afternoon, students. So, in today's class, we'll discuss electric potential. Actually, for A section, we had already discussed this topic, but I wanted to discuss this again because there were very few students in the class that day. So that, and one more point is there will be a continuity for the problems which we are solving today. So that is why I thought of doing this again. So now, uh, electric potential. So until now, whatever we have discussed is one is Coulomb's law and the other one is Gauss law, right? So in Coulomb's law, we know that we have discussed about how to find the force when when two charges are given. We will be able to calculate what is the force exerted on each other by applying the formula given by Coulomb's law, right? And the next topic what we discussed was electric field intensity, which was nothing but when we know the force F, right? Then how to find E vector? E vector is nothing but the force experienced by unit charge, right? So this is one way of finding electric field intensity. One way of finding electric field intensity when we know the force and the charge, right? That is what is written here. The method for obtaining electric field intensity is by one method is Coulomb's law, the second one is Gauss law. So when we discuss electric field intensity, we have seen various applications such as for a point charge, infinite line charge, infinite surface charge, right? And the same things were discussed in applications of Gauss law, right? So we can use both Coulomb's law and Gauss law for calculating the electric field intensity. Now in this module or in this topic, we'll be seeing how to calculate electric field intensity by using a scalar potential which is denoted by V, which is denoted by capital V. So where V is nothing but it is electric potential, right? So now consider these as electric flux lines, or this is electric field due to electric field intensity E vector, right? Now, so these are the electric flux lines due to electric field, some electric field. Now, what happens is this is the origin. This is the origin. Now, assume there was one charge at A, right? Some charge of q coulombs is at A. Now, we are trying to move this charge from A to B, A to B in the presence of this electric field. I'll repeat again. Now, there is some electric field present, which is E vector, right? Now, this is the origin. Now, in the presence of this electric field, we are trying to move this point charge or this charge of some q coulombs from point A to point B, right? So, this is the path which is shown in which the charge is moving, right? Now, we'll consider the path, we'll take the path and we'll assume this short distance or the short differential length as dl, right? Now, yeah, now this is a position vector of A. Since this is the origin, now this is the RA denotes the position vector of point A, and RB denotes the position vector of point B, right? Now this this R is nothing but the position vector of this differential length what we have considered, right? So you have to remember three things here. RA is the position vector of point A or the point where charge is located, and RB is a position vector of point B where the charge has moved from A to B, and where R is nothing but the position vector of the differential length dl, right? Now, now suppose we wish to move a point charge q from point A to B in an electric field E as shown in the figure. So from Coulomb's law we know that, from Coulomb's law what we have now, from electric field intensity E vector is nothing but force experienced per unit charge, right? So if I want force at any point is the potential difference between that point and a chosen point at which the potential is 0, right? So how did we start the derivation? Here we started the derivation by taking 2 points. Here we started the derivation by taking 2 points, that is point A and point B. So we were able to find what is the potential difference between A and B, that was given by VAB, and VAB is given by 1 by RB minus 1 by RA into these constants, that is Q divided by 4 pi epsilon naught, right? Now here, how did we get the absolute potential or potential? By taking this RA at infinity or RA at infinity, right? So this RA at infinity is nothing but it is called the reference point. So how did we denote this particular, this equation? This equation, how did we denote? By taking the reference of RA at infinity. So that is what the statement says. The potential at any point is the potential difference between that point and a point chosen at which the potential is 0. When does the potential become 0? Only when that particular charge is at infinity. When that particular charge is at infinity, RA will become infinity. So 1 by RA will be 0. So VA will be equal to 0, right? So what you have to understand here is potential difference will be calculated between exactly 2 points. So here A has its own potential and B has its own potential. So the difference between these two will be called as potential difference, right? Now, if we want to calculate what is the exact potential at point A, we have to choose one point at infinity. We have to choose one point at infinity. Now, the potential, this is called reference. This is called reference, right? Now, if you measure the potential difference between point A and this reference, which is at infinity, this will give you VA. This will give you VA. So for measuring the potential, what all you need? You need you need a point where you have to calculate the potential, and you need a point reference where the potential is 0. Only then you can calculate the absolute potential or potential. But whereas potential difference, you need two different points which has its own potential. I hope it is clear. Yes. So I'll read it again. The potential at any point is the potential difference between that point and a chosen point at which the potential is 0. Right? Okay. Now, if the point charge q is not located at the origin, but at the point whose position vector is r dash, the potential v of x comma y comma z, that is in Cartesian coordinate system, right? Or simply v of r is a function, not v into r. You have to note that at r becomes v of r is equal to q divided by 4 pi epsilon naught into r minus r dash, right? So how to understand this one? So we had an equation in the previous slide. It is only that, for the potential, not for the potential difference. For the potential, we had q, for example, at VA, we had q divided by 4 pi epsilon naught into RA. How did we simply write RA here? Because we had taken this RA from the origin. That is why there was no problem. Now, if you have some other kind of problem, or where this is the origin, right? This is the origin, and this is the origin, and this is origin, and this is the point A, right? So now you need to know what is the position vector of this particular point, and you should know what is the position vector of this particular point, right? And then subtracting those two will give you this equation. Suppose here the charge is located at this point. In the earlier case, what we discussed was, in the earlier case, the charge was located at the origin. So we were able to calculate what is the potential here by taking this RA directly, right? But here, when origin is there without any charge and the charge is located at some point R, and this particular this particular point where we have to calculate the potential is at R. So these are the position vectors, you have to be clear, and this will be R1 or R dash, right? So now how do you write? So we are calculating the potential as we discussed in the class. So final minus initial, right? Or we'll interchange these two, or else I'll explain this once more. Now first thing is, we'll consider the origin point here, right? Now we need two more points. That is, we need a point where we have to calculate the potential. So this I'll take it as point A, right? Now we need to also know where we are placing the charge. So now this is the point where I am placing the charge Q. Now what we have to understand is, we have to calculate what is the potential at A. We have to calculate what is the potential at A due to this charge Q. Now please listen this properly. In the earlier case, we had placed this Q itself in the origin. So we got the position vector of A directly, right? Now that is not the case. The origin is here. So first thing is, we need to obtain what is the position vector of this one, and then we have to obtain what is the position vector of this one, right? So now, so this should be final minus initial. So this should be R, and this should be R dash. This should be R dash. So now what will be the equivalent here? Final minus initial. It will be R minus R dash. So that is what is exactly written here, right? So now what if there are multiple charges? So now what if there are multiple charges? Suppose this is the origin. Then we'll place some of the charges. This is Q1, right? And this is Q2, and this is Q3, right? And now we'll consider one point where we have to calculate the potential potential, right? So we'll consider this point where we have to calculate the potential, right? Now all these charges will have its own unit vectors because it, not unit vectors, position vectors, because it is not at the origin, right? So first we'll obtain what are the unit vectors of the position vectors of these three vectors. So there will be n number of charges like this. I have taken here only 3, right? So now what we have to do is we have to find what is the potential. We have to obtain what is the potential. We have to obtain what is the potential at this point due to this q1, q2 and q3, right? So now this position vector of this charge will be r, right? So now this q1 also will have effect on this point, q2 and q3, right? So like this, now this is r, so this will be r1 and this will be r2 and this will be r3. So the distance between q1 and this point a where we have to calculate the potential will be, so now here you can see that q1 is, this is r1 position vector and the position vector of a is r. So final minus initial will be r minus r1, right? That is what is written here. Similarly for q2 it will be r minus r2. Similarly for q3 it will be r minus r3, final minus initial, right? So this is the equation which you have to remember if there are n number of point charges and you have to calculate a potential at one point due to all these charges. So first you have to obtain the position vectors of q1, q2, q3 and you have to obtain the position vector of this point A and you have to do vector addition or vector subtraction to obtain this equation r minus r1, right? So we'll move on to the next slide. Okay, yeah. Now coming to the next slide. So here you can see that whatever we are calculating here is nothing but the potential, right? So what is the main formula for calculating the potential? We have V is equal to Q divided by 4 pi epsilon naught into R. So if this is A and R also will be A. So if this is A, here also we'll have A, right? In general what we do, we'll just take this as V itself. Now this is a formula which we'll use only when this Q is at origin, right? So if Q is not at origin, then you have to use this formula, that is R minus R dash, which we have discussed in the previous slide, correct? And it is a scalar, that's why you don't have a unit vector. Now, so this equation you should know that this is used only for a point charge. This formula, you know that it is used only for the point charge. Now if the same formula if we have to obtain for the line charge, surface charge and volume charge, how to do that? So for that what we'll do is we know that rho L is equal to Q by L, right? Rho S is equal to Q by surface, yes. we get dq. We get dq is equal to rho l into dl. Now here in this equation, if I differentiate on both the sides, right, what do we get? I'll get dv is equal to q divided by, that is dq divided by 4 pi epsilon naught into r minus r dash. Correct. I'm just differentiating this equation on both the sides. Now if I want to remove, I mean if I want to get only v, I need to integrate this. So I'll get v is equal to integral of dq divided by 4 pi epsilon naught into r minus r dash. Correct. So that is what we have to do. Now this dq we can get different equations for different subtypes of substitution. Now for line charge, what did we get here? dq is equal to rho l into dl, right? So I'll simply substitute dq as rho l into dl. So this is the equation. This is the equation what you get for line charge when I substitute dq as rho l into dl, right? So this rho l of r dash is nothing but at this particular point r dash, what is the line charge density? That is why it is written as a function, right? Now next one, that is for the surface charge, the same thing. The same equation is used for everything here. Now dq, how can we write for surface charge? It is rho s into ds. For volume, it will be rho v into dv, right? So you need to remember all these kind of charge distributions, right? So we'll move on to the next slide. Now one more important topic in this module, that is relationship between E and V, that is electric field intensity and the potential V, right? Here you have to note that E is a vector and the potential is a scalar, and it is also known as, this relation is also known as Maxwell's equation. Now we'll consider one diagram here, that is we have electric field E, right? Now here point A is moved, I mean the charge is moved from point A to point B in the presence of this electric field. So this is one of the path and this is the other path, right? We have two paths here, one path and the other path. Now just read this line. The potential difference between points A and B is independent of the paths taken. That is what I explained in the first part of the lecture today. So from A to B, however you move, it can be a straight line or you can move from one point to the other point in any path. The work done will be the same, right? So the potential difference and work is directly proportional. So potential difference between points A and B is independent of paths taken. Hence, VBA will be equal to minus VAB, right? Or if I take it to this side, I'll get VBA plus VAB is equal to 0, right? Now here, what you have to note that, what is this equation? We have E vector dot dl vector. We have discussed this in the beginning of the class. That is this equation. So here I am showing you again, that is the potential difference equation, that is E vector dot dl vector. So the same formula is used here, and here you can see that we have used a closed integral here, that is this symbol. That means over a closed path, that is VAB plus VBA plus VAB is nothing but it forms a closed integral. So over a length, E vector dot dl vector is equal to 0, right? So the potential difference is independent of the path taken. That is why over a closed loop of length, E vector dot dl vector, which is nothing but the potential difference, will be equal to 0, right? So this equation is very important here. Now coming to the next line, so applying Stokes theorem. This Stokes theorem will be discussing in detail in magnetostatics. Magnetostatics will be discussing this Stokes theorem in detail. So as of now, you just see it as a formula. So what we have here is closed integral of E vector dot dl vector is equal to surface integral of curl of E vector dot ds vector. Right? This formula is important here. Now, in the previous slide, what we have this equation E vector dot dl vector, and from Stokes theorem on the right hand side, we have surface integral of curl of E vector dot ds is equal to 0. So since this equation is 0, we can take this curl of E vector also as 0. Curl of E vector also as 0, right? So vectors whose line integral does not depend on the path of integration are called conservative vector fields. This is very important. So line integral from one point to the other point can be a straight line or through some other path like this from point A to point B. So this is one path and this is the other path, right? But here the potential difference will be the same. It is independent of the path taken, right? So these kind of vectors are called vector fields. These kind of fields are called vector fields. So now what you have to note here is we have E vector dot dl vector is equal to 0 as one equation. It is called Maxwell's equation in integral form. And curl of E vector is equal to 0. This we got by using Stokes theorem. So it is called Maxwell's equation in differential form. This is also called Maxwell's equation in point form. Point form, right? You have to note this one. Now going to the next slide. Yeah, going to the next slide. Now here we know that the potential is given by V is equal to minus E vector dot dl vector, and it follows that dV is equal to, by differentiating on both the sides. So this integration sign will go off. So we'll get dV is equal to minus E dot dl, which is nothing but this E, or this E is a scalar now. It'll have all, vector, it'll have all three components, Ex. So this E vector will have, how do we write this? Ex Ax cap plus Ey Ay cap plus Ez Az cap, right? This is how we write the equation for E. Now how do we write the equation for dl? Now dl vector is equal to dx Ax cap plus dy Ay cap plus dz Az cap from Cartesian coordinate system. Now if you find E vector, so this is E vector dot dl vector, what happens? Now we get Ex into dx, Ax dot Ax will be 1. So only Ax dot Ax will be 1, Ax dot Ay, Ax dot Az will be 0. So we get this equation. Now, so from calculus of multivariables, we have dV is equal to, you have to note this formula here, dV is equal to dou v by dou x into dx plus dou v by dou y into dy plus dou v by dou z into dz. So this is from calculus and this is from E dot dl, right? When you compare these two, what do we get? In place of dx here, we have dx here, right? Here dy, and here also we have dy, and here dz, and here also we have dz, right? So now minus Ex can be equated to this, Ey can be equated to this, and Ez can be equated to this. So that is what exactly is written here. Ex is equal to minus dou v by dou x, Ey is equal to minus dou v by dou y, and Ez is equal to minus dou v by dou z. Now if you remember the formula for the gradient of V for Cartesian coordinate system, we have dou V by dou X plus dou V by dou Y plus dou V by dou Z, right? So here we have a negative sign overall, so that is why we can write E vector. E vector is equal to minus gradient of V. This is one of the very important derivation in this module. You may get a question as show that the electric field intensity is negative gradient of V, right? So you should know this derivation properly. That is, the electric field intensity is gradient of V. The negative sign shows that the direction of E is opposite to the direction in which V increases, right? E is directed from higher to lower potentials of V. This is very important. You should note this. So the negative sign shows that the direction of E is opposite to the direction in which V increases. In which the direction of, in which V increases. So this you should note. These points are important. Now, so we'll just recap what all we have discussed. So we started with electric potential and we came to know that electric field intensity can be calculated, whichever methods we know as of now are Coulomb's law and Gauss law. So electric field intensity can be calculated also using the scalar potential V, right? And then we started with this derivation and we obtained the equation for potential difference VAB, which is nothing but minus minus integral of A to B E vector dot dl vector. And then we came to the potential V is equal to Q divided by 4 pi epsilon naught R. So if it is not at the origin, if the charge Q is not at the origin, then these are the formulas. And if there are multiple charges which are not at the origin, you have to use this formula. We have seen the explanation for this. Next, we have seen what are the formulas for potential for various kind of charge distributions. Then we have seen relationship. We have seen the relationship between electric field intensity and the potential V, which is called Maxwell's equation. From this, we obtain two equations. One is Maxwell's equation in integral form. The other one is Maxwell's equation in differential form. And by using V is equal to minus E vector dot dl vector and calculus, we obtained that the electric field intensity is minus negative gradient of V. Negative gradient of V. Okay. So now we have seen that the electric field intensity is negative gradient of V. Now coming to the next topic, that is energy density in electrostatics. Energy density in electrostatic fields. So now if you see here in the syllabus, what we have here is one second. Yeah. Now here you can see that in module 2 we have potential, potential difference, potential gradient. So these three things we have discussed now. So we'll solve some problems based on this in the next class because we are running out of time. Only 9 minutes left for an hour. So then we'll start with energy in electrostatic field and energy density in the next class. That is energy density in electrostatic fields we'll discuss in the next class, right? So what we'll do is we'll discuss the theory part first, and then we'll come back to the problems, right? So now for all the classes, you have to obtain, a Google form will be shared to your shared in your Google Classroom for electromagnetic field theory, and it will be opened only during my hours. So what you have to do is you have to just enter the name and USN, so that will be taken as the attendance, right? So the attendance will be considered only for the first 10 minutes. So you have to enter your name and USN within 10 minutes. After that, if you are entering, it will not be considered for the attendance, right? So from the next class,